Hey everyone, back in a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will continue with our videos about energy, but we will start talking about a more complicated quantity, potential energy. If you haven't watched our first videos about work and kinetic energy, go watch them now so that you can understand every explanation we will give in today's video. Today, we will first introduce what potential energy really is and where it arises from. After that, we will formulate mechanical energy from a combination of kinetic energy and potential energy. And finally, we will formulate mechanical energy conservation and explore what happens with non-conservative forces. So, let's start! So, what is potential energy? Recall from our last video that work equals the integral, the path integral, from a point A to a point B of a function, the force, times ds. So, if the force is conservative, recall from last time, Fz conservative, that is the exact same as saying that the work is path independent. Therefore, what we know from this is that work is not going to depend on the path you take. So it's going to be a function, we'll signal it by f, from the point B, minus a function from the point A. And it's going to be the same function evaluated at those points. It's just going to be the antiderivative of that function. Now, we are going to give this function a fancy name. We'll call it potential energy, and we are going to signal it by U. So we'll say that this is equal to U at B minus U at A. Rearranging the terms, we find that taking that minus outside, this is the U at A minus the U at B, which means that what we have over here is a change, is the change in this quantity that has happened when growing from A to B. So we'll signal it by a delta, the change in U. Therefore, we reach the conclusion that work equals minus the change on potential energy. And we will later continue exploring this notion and see where it leads us. But first, I want to give you some intuition about what we have done. Work is a quantity that relates different points and the energy required from going from one to them to another one. Therefore, this function is a measure of how energetic a point is. And what this allows us is that if, for example, we draw a graph of some potential energy, what we can see is that this point is less energetic than this one over here, and that this point is the lowest energy point of this interval we have drawn. Furthermore, we see that what really matters is the change in potential energy. there is not a 0 point really defined, and we will take that as an advantage to define it in the best way, in the way that fits more the math and makes it seem more simple. Sometimes it will be at infinity, sometimes it will be at 0, so we will work with that and we will choose it. That also means that we can slide this graph up and down and it doesn't matter, because what we really care about is the change in potential energy. In a sense, this can remind you to, for example, a hill, and if you draw a ball on it, you know that the ball will go to the lowest energy point it can. So it will fall towards this side. And the reason why this reminds you of that situation, because a ball on a hill is the exact same thing. Height is proportional to potential energy, or better, potential energy is proportional to height near the surface of the earth, as we will see in the next video. Therefore, imagining this situation as a ball in some hills, that is the function of potential energy, is the exact thing that is happening, because a ball in some hills is a ball in a difference of potential and moving. So we have just found that work equals minus the change in potential energy. And from last time, we know that work equals the change of kinetic energy from the work kinetic energy theorem. Therefore, equating both sides, what we find is that delta K equals minus delta U, and therefore we see delta K plus delta U equals 0. This, in a sense, helps us define some quantity that somehow takes account of both what kinetic energy you have and what potential energy you have. In that way, we're going to define this as 1/2 m and the velocity at a point A square minus 1/2 m and the velocity at a point B square. Let's say we go from point A to B so that things are simpler. And we will have also a potential energy going at B and a potential energy that we had an A, and this is equal to 0. So if we get all the A quantities to that side, we get that 1/2 m squared plus UB equals 1/2 m BA squared plus UA. And this gives us a sense about a quantity that is important because it's conserved in between these 2 points. So that leads us to define mechanical energy, E mechanical, which is going to be equal to the kinetic energy at some point plus the potential energy. Or if we express it in a more expanded way, this quantity, the mechanical energy at A is going to be equal to this, and it will depend on the potential. Note that that property of potential energy, which we were talking about before, that there is not a 0 point energy, is going to translate into mechanical energy. Depending on where do we define this potential energy to be 0, we're going to have a different point for which the mechanical energy is going to be 0. It's going to take another value. So really what we are not going to care that much about is about the absolute value of this energy. We're going to care about changes in energy. So we define the change in mechanical energy to be this quantity, delta K, the change in kinetic energy, plus the change in potential energy. As some of you may have already noticed, this, if we substitute it in here, we will get that mechanical energy equals 0. But on our daily experience, we don't experience this. This is what is called the conservation of energy, the conservation of mechanical energy. However, for example, if we are in a hill and we had our ball, we know that our ball may go and may oscillate from here back and forth a couple times, but we know that at some point it will end up stopping over there. And that is breaking conservation of energy, because at this point it will have less energy and it will have no kinetic energy. So it will have a total less amount of mechanical energy, and the change would not be equal to 0. That is where non-conservative forces enter the game. We have defined this potential energy quantity for conservative forces, for a work equal to the work created for conservative forces. But there's also some work we will need to do to deal with non-conservative forces. And this is really what it's equal to the change in kinetic energy. Therefore, what we find is that this work conservative is indeed equal to minus the change in potential energy. But we have this component that wasn't before, and is usually represented, as we talked about in other videos, as friction. Friction is the reason why this ball stops and why the change in mechanical energy is not 0. If we solve for the non-conservative work, we find is delta U plus delta K, which is the change in the mechanical energy. So what we see is that mechanical energy really does change and is not conserved when there is non-conservative forces in the game. Some of you may be wondering, but what about the second law of thermodynamics that says that energy is always conserved? Why is it not being conserved here? Okay, so in friction, what is really happening is that this energy is being transferred to the materials as thermal energy, and the mechanical energy doesn't take into account that. That's why we can lose some mechanical energy which is being converted to other types of energy. And in that sense, energy is conserved. Just not only mechanical energy, we need to consider more types of energy. That is all for today. I hope that you got a sense and understanding of what this potential energy really is, and also how it can vary its 0 point as it's not really defined, and how it's related to this quantity, this new quantity we defined of mechanical energy that is in some cases conserved. In the next video, we will explore some scenarios in which we can calculate as a function what the potential energy is. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!